What is this?
0.
What's this?
1.
What's this?
One.
Is it 1 or is it 0?
It's 1.
Okay, you stood your ground. Very good.
Yeah.
Yes. So surprisingly, x to the 0 is 1, not 0. And what's this?
Just x.
Not 1. Okay. So how would you describe this in words? Well, I would say that what this means is 0 to any power is 0. 0 to any power is 0. So how would you describe this in words?
1 to any power is 1.
Yeah. So what would this be?
1.
Yeah, it doesn't matter how weird it looks. 1 to any power is 1. That's maybe not 100% obvious, but it's true. How would you describe this in words?
X to 0. 0. X raised to 0 is 1.
Good. That's not quite as intuitive as what we said over here. So remember, we've said this. What this means practically is 1 to any power is 1. So how would you describe this in words without using the word x?
So any number that's raised to 0 is 1.
That's what I was going for. Yeah. Because you're probably not going to see x to the 0 on a problem. You're going to see something else to the 0. So we need to know what this means is anything to the 0th power is 1. And how would you interpret this in words?
And so if you have some number that's raised to 1, it's just that number.
Yeah, anything to the first power is just that same thing. Okay, good. We've already seen how those come up a lot in this section, but we'll be coming back to that too. All right, here's an algebraic expression. So I'd like you to work on this on your screen. Try to come up with some other way to write this expression. Try to come up with some other way to write this expression on your screen.
Okay.
Okay, so what you did here is you took a single fraction and you rewrote it as 3 separate fractions. How could you check that that was legal?
If we add them all together, we should get this.
Right, does that work?
Yep.
Yeah, because they have a common denominator. Okay, why are you better off with 3 fractions than 1 fraction? Isn't that moving backwards? Well, the point is that the 3 fractions are each simpler than the one you started with, so it might be helpful to do that. Okay, and then it looked like you canceled the b from the second term, and you canceled 1b from the third term. And you saw you couldn't cancel any b's from the first term, so that was good as well. Okay, good. All right, so that's some algebra that we'll be needing. So that was a good approach. Excellent. I'll go back to my screen. Now let's try this problem.
Okay, so so you add 2 over 2. That gives you 1 over 2. Divide by 1 over 2, which is really 2x with 1/2. Okay. Then f of b minus f of a. I'm going to check this on my calculator. So y equals 1 over the square root of x graph that. And then I'm going to get a second calc. Set on 7. Type in my lower limit as 2. Upper limit as 5. That's what I get. Cool, so that's the answer.
Let's see.
And my notation was a little poor, but I guess I'm not comfortable with it yet, and it was still on the upside. Just threw it out for now.
Okay, yeah, all right. I ended up with the same answer as you there, 1.64, and that's good that you checked that on your calculator. Okay, so that was the correct answer, and that was also a good process for solving that problem. Let's go back to my screen. So that was the correct answer, and it was also a good process, but as you mentioned, it wasn't the best notation. So let's go through what would be a good notation for this. So the first thing you did here is you took this expression and you rewrote it like this, which was excellent. That was the exact right thing to do. Now, have we taken the antiderivative yet?
Nope.
So the key thing that was missing from your notation is we should still keep writing this definite integral sign until we've taken the antiderivative.
Okay.
We should keep writing this. This is similar to how when we were taking derivatives, we have to keep writing the prime symbol until we've taken the derivative. All we've done is re-expressed what's inside of the integral. We haven't taken the antiderivative yet, so this was the notation we need. And then we can go on and write that like this. So then you rewrote it like this. So it looked like a standard power function. So have we taken the antiderivative yet?
Not yet.
So we still have to put in the integral sign. Then you took the antiderivative. So have we taken the antiderivative now?
Yep.
Yeah. Okay. So the next thing, now I went back and rechecked how your instructor writes these, and your instructor is using the same notation that I've been using, a little different than yours. I think it would be better to shift to how I've been doing this on my screen without writing the f of b minus f of a, because that's more consistent with your textbook and with how your instructor writes it out. And I think as the problems get more difficult, that this will be a better notation. So when we take the antiderivative, here's how we do it. Since we've taken the antiderivative, we don't keep writing the definite integral sign anymore. But we have to write this bracket to show that we're going to have to evaluate this in 5 and 2 and subtract them. This really just means the same exact thing as you've been writing. This means evaluated at 5, evaluated at 2, and subtract them. But this is the standard way it's written. I think this will be better for us for doing these problems. So then we would have 2 times 5 to the 1/2 minus 2 times 2 to the 1/2. That's the same calculation you ended up doing, just with a slightly different notation. And also, I think a better way to do these is to keep writing them as equations with left and right sides, so we know what we're focusing on here. What goes over here?
What's above? So
yeah, this thing above. And what goes here?
The same thing.
Yeah. So we can just use a ditto sign to save time. We should probably rewrite that here in the final line to remind ourselves what this left-hand side is. And now we can see that we've clearly solved what the question was asking. Okay, so I think this is the notation that your instructor uses and your textbook uses. I think this will be the best way to do these types of problems. So we'll try to move into this notation in today's session. Okay, but aside from the notation, your process was a good one, and your answer was correct. This was a good two-step process of rewriting the expression before you took the integral. Okay, good. So I'll move back here. So let's try this. Okay, let's try this problem.
Well, so 3 divided by 3. What gives us cosine of t?
What's the antiderivative of 2 times t squared?
It's going to be 2/3 t squared.
How did you explain?
Sorry, cubed.
Okay, could you say that again?
2/3 t cubed.
Okay.
I messed up.
Okay.
I guess I will figure that out eventually. Okay. So we're going to change this one. Minus sign. See. Okay, this is what I get.
Okay. Now let's talk about this a little. Your first line, I guess we have to get used to this notation. Your first line has a brackets, and you got a pi over 2 and a 0. What do those brackets mean with the pi over 2 and the 0?
We're subtracting.
Right. Oh, okay. Now, you didn't write that down. Was there any particular reason why you didn't write down the subtracting the 0 part?
Because it's just zeroed out.
Okay. Okay, that's fine. I didn't realize that myself, but as long as you saw that, you can leave that out. Okay, fair enough.
But I guess maybe it's safer when you're dealing with...
I think it would be better to write it out and then put in zeros for that. Because it's always easier to check your work if your work is on paper instead of in your head. if you write it down on paper, then you can check that it really is 0. So yeah, it's definitely a good idea to zero those out, but we should probably write them down to start with. Okay?
And that's the answer, and I'm going to check it real quick. So y equals 2x squared minus cosine of x graph. And now I'm going to go to second calc 7. Lower limit of 0 and upper limit of pi over 2. And I get a different answer. So let me see if I put my function in right. 2 x squared minus cosine of x. Okay. So the antiderivative is 2 plus 1 is 3. So 2/3 e cubed minus what gives it cosine. The derivative of sine is cosine. Okay, so that's good. Plug in top number 2. We have name the calculator. So 2/3 times pi divided by 2 cubed. I bet I squared. Okay, minus. Oh. Yeah, I did. That was my issue. Okay. 2/3 times pi divided by 2 cubed minus sine of pi divided by 2. Yep. Okay.
Okay, so you got the same answer now as your calculator?
Yep.
Okay, so that's certainly useful to be able to check our work there. What went wrong? Can you see what went wrong the first time you did that?
Yeah, and instead of putting in a cube, I put it squared.
Oh, okay. So that was the original problem that we'd had here of having the incorrect exponent. Okay. All right. So that's good that you checked that, and then when you saw that you'd made a mistake, you were able to go back and to check your work. Let's see. Okay, good. I'll go to my screen. So let me write out one way you might think about this problem. What you're really doing on this problem is this. Well, actually, I really want to do that on this problem. Maybe not. All right, we'll stick with your answer. All right, so okay, and I forgot to check, but did you you wanted to be careful here to use t's and not x's? Okay, well, actually, I think we did about the best we could with that problem. Okay, fair enough. All right, so we did make a careless mistake on that problem with the exponent, so that's where the practice comes in, and also a careless mistake with the exponent again on the calculator. So again, it's important to do a bit of practice with those problems, but it's good that you caught the mistake on the calculator. Okay, well, I think we can move forward then. Let's figure out what this is.
1.
Looks like you had that memorized.
Yeah, that's big foundation. 0 is 1.
Good. Okay, so we said here that the cosine of 0 is 1. Check that on your calculator.
True.
Excellent, thank goodness. Do you know what this is?
It's the inverse of cosine of 1, so it would be 1 over the 1 over the negative square root of 1 minus x squared, so 1. I'll write it out.
Okay, it sounds like you're thinking of something like this.
Right.
Okay, this actually would be a false statement. Here's what I think you were thinking of.
Okay.
So this expression does not calculate inverse cosine. It calculates the derivative of an inverse cosine. Oh, so actually you'd have to write it then like this. If you're taking a derivative, you'd put in an x here, not a 1. So it's important. Do you see the difference between these two lines?
Mm-hmm.
Yeah, so that's a very important distinction not to confuse with each other. It's just the same as is this true or false?
False.
Why would anyone think this was true? How can I change this to make it true?
You can write x cubed prime,
Right.
and then it'll be true.
So the power rule doesn't say that x cubed is the same as 3x squared. It says that the derivative of x cubed is 3x squared. Well, the same deal over here. The derivative of inverse cosine is 1 over negative root 1 minus x squared. That doesn't mean this is a way to calculate the inverse cosine. All right, so that's an important confusion for us to clear up. All right. Let's try again. What's the cosine of 0?
1.
So how would we find the inverse cosine of 1? Well, remember, the whole point here is that this is the inverse cosine. It undoes cosine. It's an inverse function of a cosine.
Okay.
If you start with 0 and you take its cosine, what number do you get? If you start with 0 and you take its cosine, what number do you get?
1.
So if you start with 1 and take its inverse cosine, what number do you get?
0.
That's right. That's the whole definition of an inverse function. This is something you and I never really talked about before. In the past, whenever we used this as inverse cosine, we didn't really say what the heck it means to be an inverse cosine. We were just treating it like, I don't know, some function that we had no idea what it meant. But hopefully now we have a slightly better idea of what the inverse cosine is. It undoes cosine. So it's like the relationship between squaring something and taking the square root, or the relationship between adding 4 and subtracting 4, or the relationship between multiplying by 8 and dividing by 8. If you multiply 8 and you divide by 8, you get back to where you started. Well, if you take the cosine and then you take the inverse cosine, you get back to where you started. So hopefully this gives us a slightly better idea of what the inverse trigonometric functions mean. Now, what type, let's see. What type of input do we put in for cosine? The input for a cosine, we haven't really talked about what these inputs stand for at all. I think you said you haven't actually really taken trigonometry, but the inputs for inputs for trigonometric functions are angles. The inputs for trigonometric functions are angles. Now, what are the units we use to measure an angle? Well, you might remember that sometimes we might use degrees to measure angles. However, we don't use degrees in calculus. We don't use degrees in calculus. In calculus, we use radians. And the way this works, do you know what 360 degrees means?
Circle.
Yeah, that's just a complete circle. Well, it turns out that 360 degrees is 2 pi radians. 360 degrees is 2 pi radians. So 180 degrees would be half a circle. How many radians would that be?
1 pi.
Right. because 180 is half of 360. 90 degrees is a right angle. So how many radians are there in a right angle?
1/2.
Right. And these numbers are not as obvious, but this would be pi over 3 radians. This would be pi over 4 radians. This would be pi over 6 radians. How many radians would this be?
1/8.
I think you're getting a little confused. So if you have 0 degrees, that would also be 0 radians. Because that means that you haven't 0 degrees would mean no angle at all. 0 degrees would mean no angle at all. Well, if no angle at all, we would have 0 no matter what our units are. Okay. Well, one thing to notice here is that when you measure things in radians, pi pops up a lot. That was one of the main points I wanted to make here. So it's probably not necessary for you to memorize these, although, you know, it wouldn't hurt to know this, say. It wouldn't hurt to know this, but we don't need to memorize these, but we should know that when you measure things in radians, pi pops up a lot. Angles, so pi pops up a lot when we're measuring angles in radians. That's my main point here. So let's figure out, say, the cosine of pi over 2.
So the cosine of
I'm sorry, could you repeat that?
the cosine of 90.
Well, it would be the cosine of 90 degrees, but your calculator is already in radians mode. So I didn't want to mislead you here. We're not going to actually use degrees for our problems. We're not actually going to use degrees. We're just going to keep doing cosines the same as before. I just wanted to point out to you that all along we've been assuming everything's in radians. You might have already seen some problems that use pi. So how would you calculate the cosine of pi over 2?
0.
Good. How did you figure that out?
That's the cosine of pi over 2.
In your calculator?
Yeah.
Okay, good. I can't hear you that well, but all right, good. So that would give us this. Now then, what's this?
The inverse cosine of 0.
Now, before you put it in your calculator, is there any way to figure this out?
Sure there is.
Using what we were talking about a few moments ago. Remember that inverse cosine reverses cosine. They're inverse functions. Let's go back up and review this example. The cosine of 0 is 1. So what's the inverse cosine of 1?
0.
How do you know?
This pattern.
Well, the point is because it takes us back to where we started. If the cosine of 0 is 1, then when you take the inverse cosine of 1, that should take you back to the number that you originally started with. So if the cosine of pi over 2 is 0, using that pattern, what's the inverse cosine of 0?
Pi over 2.
That's right. Do you see the point here, how it reversed what you did? If you take the cosine of pi over 2, that gives you a number. And then if you take the inverse cosine of that number, that takes you back to where you started. Okay, so, but you're right. Normally, the easiest way to find inverse cosines is on your calculator. So go ahead and use your calculator. Talk me through how would you work that out on your calculator.
Second cosine 5 divided by 2.
Take your time. Remember, what's the problem?
Second cosine 0.
Yeah. So 0 is the input here. And what do you get?
1 second. 1.57.
Okay, good. Now, I think it might be better in our answers to give our answers exactly. So you've gotten here 1.5. So I think your instructor, this is how your instructor reports their answers in the answer key. I think they might be looking for this on the test. Now, the problem here is this is probably a function of pi, right? I guess that was the main point that I was trying to make. When you take inverse cosines, you usually end up with a function of pi. So how could we figure out what that is? Well, we can take our answer, and you can see the calculator on my screen, right? Take the answer and divide by pi. We get 0.5. So that gives us this equation. we know that our answer divided by pi is 0.5. How could you solve this equation for the answer?
Multiply.
And what do you get?
1/2 pi.
Yeah, we get the answer is 0.5 times pi, which is 1/2 pi, or pi over 2. So I think this is how your instructor wants you to give the answers for the inverse cosines and for the inverse trig functions. This is how your instructor always gives the answers in terms of pi. So that's the main thing I wanted to go over here. The main thing I wanted to go over is if you think there's a pi in your answer on the calculator, you can work that out by dividing the answer by pi. Notice it wouldn't have done you any good to try to change this into a fraction. If you just tried to change it into a fraction, you would just get gobbledygook. It won't change into a fraction because it's not an even fraction. Instead, you have to take the answer. If you think there's a pi in it, you do this. How would you know there's a pi in it? Well, we just need to kind of memorize that in the output from inverse trig functions tends to have a pi in it. The output from an inverse trig function tends to have a pi in it. And then you can work out what that means on your calculator by writing down a little equation like this. We saw that our answer divided by pi was 0.5, so then we can figure out how to write that answer. Okay, so here's the point we were making. The input to a cosine is an angle. And the output from a cosine then is just an ordinary number. But the inverse cosine is the inverse of cosine. So since the input to the cosine is an angle, the output from an inverse trig function is an angle. The output from an inverse trig function is an angle. The output from an inverse trig function is an angle. And what units do we measure angles in this class? Radians. And what number often appears when you're measuring in radians?
Pi.
So that's my point. The output from inverse trig functions often is a multiple of pi. Let's write that down. Not always, but often. So if you're doing an inverse trig function on your calculator and you get a complicated decimal, it's often a good idea to try to divide that by pi so that you can get an exact answer. Would this work for trig functions? Is the output from a trig function often a multiple of pi? Well, no. The input to the trig function is a multiple of pi, but not the output. Okay. Tell me when you have that down.
Yep.
So which of these is often going to be a multiple of pi?
The first one on the left.
Do we expect this to be a multiple of pi?
No.
No. So which of these is often a multiple of pi?
The one on the right.
Yeah, the output. Okay, so would we expect this to be a multiple of pi?
Nope.
No. I've been using these terms input and output. So are those terms clear? Is this an input or an output?
Input.
How about this?
Output.
How about this?
Input.
And how about this? Output. Okay. Okay, all right, so this right here is the main point I wanted to make. This right here. The output from inverse trig functions is often a multiple of pi, so you can get an exact answer on your calculator by dividing your answer by pi, is my point. So that's the main point. This here, I was just trying to give you some background into why it's a multiple of pi. The reason why it's a multiple of pi is because the output from an inverse trig function is an angle. The output from an inverse trig function is an angle. Angles in calculus are measured in radians, and radians are often expressed as pi. But that was really all just background. What we're going to need for solving problems is just this idea here. The output from inverse trig functions is often a multiple of pi. Okay? All right, so talk me through how you would calculate this.
Okay, so 2 inverse cosine of 0.5. I'm going to use my calculator. So put in 2 times second cosine 0.5 equals 2.0943. I'm going to divide that by pi. That gives me 0.666. So I'm going to set up an equation that's that's 2.0943.
So instead of doing that, you could just write down, if you can look still at my screen, you can just call that the answer.
Okay. Divided by pi is equal to 2/3.
Good. So it's good that you didn't write down 0.666. You wrote down 2/3. Great.
So the answer is actually 2/3 pi.
Good. So what should I write here?
2 pi over 3.
Or 2/3 pi. Excellent. Good. Okay, good. So that's the technique to give the answers the way your instructor is giving them in the answer key. I think they might be looking for that on the test. That way we have an exact answer. How did you know to divide by pi here? It doesn't look like pi. How did you know that this is a good case to divide by pi?
Because it's the output of an inverse trig function, and we're expecting pi as an answer. And so,
right.
Yep.
Good. Excellent. Very good. Now let's calculate this.
Okay, so I'm just going to type in my calculator cosine pi over 3. That gives me 0.5, and that's it. That's the answer. Or
yeah, that was kind of a boring. That was kind of a boring problem. Let's try this problem. Nah, I changed my mind again. Let's try. Let's try this problem.
Okay, cosine of 0.8 gives us 0.6967. I'm going to see if I can make this a fraction. I can't. So
so can we should we divide this by pi to see if it's
No.
a function of pi? No. Why not?
because this is the output of a trig function, not an inverse trig.
Okay, that's all I was going for. That's right. So in this case, I think we're just going to have to accept that we just are only going to have an approximate answer. And we'll just have to write down that this is our answer. Okay, good. So that was the point I wanted to make here. We only expect the answer to be a multiple of pi when it's the output from an inverse trig function, not a regular trig function. All right, and not every output from an inverse trig function will be a function of pi, but that happens a lot. So that's certainly something that's worth checking for. Okay, good. Okay. So let's give this problem a shot.
Okay. Okay, so we can just so what gives us the derivative of inverse 3x? This is
All right. Are you working this out on your screen or on paper?
on my screen.
Okay. It's frozen up. It would be good if I could follow along so that I can make sure we're on the right track there. Maybe I'll try hanging up and calling you back again.
Okay. So we can do inverse tangent. 0.55. That's 0.466 divided by pi.
Maybe before you do that, you should complete the entire calculation. Or I don't know. Maybe not. I don't know what to do. Why don't you? I think we'll probably be better off. Why don't you try doing that whole thing in one step?
Okay. Inverse tangent of 0.55 minus the inverse tangent of 0. Okay. I get same answer, and divide that by pi. I get it 0.475.
It didn't really simplify, did it?
Right.
Okay. So in this case, we'll just have to write our original answer.
Okay.
All right, so that trick I gave you doesn't always work. In this case, the best we can do is just write down that as our answer. Okay, fair enough. All right, the main important thing here is that you saw, we haven't talked about this for a while, but how do we find definite integrals? We find definite integrals by taking the antiderivative. And what's the antiderivative of 1 over 1 plus x squared? It's inverse tangent. So it's good that you remembered that. You haven't done a problem like that for a while. You used a good use of the notation that we've been talking about here. Okay, excellent. So that's a good answer, and I guess we may as well check that on your calculator.
Okay. So y equals 1 over 1 plus x squared. Graph. Second count. 7. 0 to 0.5. And the answer is 0.46. Actually, I shouldn't. I was wrong. Okay.
Oh, I think you wrote the incorrect answer down?
Right.
Yeah. What you actually had was, so the other way of writing it, you could have said the answer was 0.147 pi. You could have said it was 0.147 pi, but since that wasn't simpler, it was better to go back to our original answer.
Yeah,
Okay.
it was just a mistake. I didn't do that.
Okay. All right. Now, I think the calculator got the same answer? All right. So again, it really helps to have the calculator to back us up here. Notice, though, one thing is the calculator will never simplify this into terms of pi. So the only way to compare your answer to the calculator answer is as a decimal. Okay. All right. That's good. All right. Good. That was a good process. You got that right. Oh, well, let's see. So next, so maybe we'll stay on your screen to not put a stress on the system. So let's give ourselves some more space. And I will verbally describe to you the next problem. So the next problem is the definite integral of 3 So the function in the middle is 3 over root 1 minus x squared. 3 over square root of 1 minus x squared. So the square root extends over that whole thing. And let's say that that goes from, say, 0 to 0.5.
Okay, so you can rewrite this as 3 Okay, this is inverse sine. And it was not necessary brackets, but okay. All right, so inverse sine of 0.5, 0.5235. Let's divide by pi real quick. And we get 1, I think that's 1, 6 times it by 6. Yep. Okay, so this answer is 1, 6 pi. Let me just double check that. 1 divided by 6 times pi should give me 0.5235. Yep. Okay. So then the negative, the inverse sine of 0, which is 0. So this answer is, what's 1/6 of 3 over 6, so 1/2 pi. Let me check this. Y equals.
Now, before you do that, you're going to have to convert your answer into a decimal so that you can compare it to what the calculator is going to give you, right? Because the calculator is going to give the answer as a decimal.
It's going to be half a pi, so like 1.57.
Okay,
like
good.
That. So y equals 3 divided by square root of 1 minus x squared graph. And then second calc, 7, 0 to 0.5. Yep, 1.57. Cool.
Okay, good. Okay, and so one thing you used here that we talked about is you can also, you rewrote your answer in terms of pi, which I think is what your instructor is going to be going for. Good. Now the way you did this is you found the inverse sine of 0.5 and converted that immediately into a multiple of pi. That might be the best approach for this. You can also do this all in one swoop and then convert it into pi. So you'll have to decide on each problem which approach is going to be better for you. I guess you have to use a little bit of judgment for that. Okay, but that was a good process. So you handled, one thing you handled well here is the 3. You used what we call the constant multiple rule for integration. The constant multiple rule for integration is you just kind of basically take the 3 out of the antiderivative and you just found the antiderivative of the 1 over 1 minus root x squared, and you just put the 3 in front of the brackets. That was a good move to put the 3 in front of the brackets. That's something that's legal with constant multiples. Okay, well, let's give ourselves some more space.
Okay.
And we'll do another problem. And yeah, since the internet connection is weak, instead of going back to my screen, I'll just describe the problems to you.
Okay.
So the next problem is the integral from 1 to 9. And then it's a fraction. On the top of the fraction, we have x minus 1. And on the bottom of the fraction, we have square root of x dx.
Okay.
Okay, so let's try this one.
X to the 1/2 x to the negative 1/2. Okay, and then so this is going to be, so when we do this, we add these exponents. Okay, so 3/2 divided by 3/2, 2/3 x, 3/2 minus plus 2/2, so 1/2 divided by 1/2, 2x, 1/2. We add 2, so 1/2, divide by 1/2, flip it, 2x. Okay. So now 2/3 times 9. Oh, I need to put in parentheses. Okay, parentheses. 2 divided by 3. 2 divided by 3 times 9 raised to 3/2. Put that in parentheses. Minus 2 times 9 raised to 1/2. Then I'm going to close off my brackets. Minus new brackets. 2 divided by 3 raised to 3/2. Minus 2 raised to
Okay,
1/2.
so let me interrupt you there. Let's see. So going back to the previous line, you had a 9 and a 1 next to the brackets, right?
Mm-hmm.
Now, so what you do in the next line is you plug in a 9 and you plug in a 1. Now I can see where you plugged in the 9, but I can't see where you plugged in the 1.
Right. Well, it's because...
So let's write out, so let's not skip any steps. Let's actually write down the number 1 that we're plugging in. You might have some simplifications that you can make, but we don't want to make those simplifications in our head. It's always easier to check your work if you write down more steps on paper. So let's write down that we're actually plugging in the 1 before we simplify.
Okay, so...
Okay, Now check your exponents there. So you have 2/3 times 1 to the 1/2 power.
Yep.
Where did you get that 1/2 power from?
Right here.
Let's see. So, but that's the second term in the brackets. That's not the term with the 2/3.
Okay. I'm just losing my bearings, I guess. Okay.
So this is something that came up maybe once before. I think we're confusing two different subtractions. There's a subtraction inside the brackets, and then we're subtracting the two brackets. So when we do this new expression, we have to go back to the beginning of the brackets. You were kind of already seeing that because that's why you wrote in the 2/3. You wrote in the 2/3 because you were going back to the beginning of the brackets. You just looked in a little bit the wrong place for the exponent. Okay. All right, so now we have that written correctly. So now what?
Now I'm going to continue on.
Okay. How so?
So I'm going to see. I'm going to do some math, and I'm going to use my calculator for it.
All right. Before we go to the calculator, let's try simplifying that second term in the brackets. How can we simplify that second term, the term in the second brackets? Let's try writing this out one more time, simplified. The first term can only be done with a calculator, but the second term we can simplify a little without a calculator. We can't simplify the first term without a calculator, but that 2/3 times 1 to the 3/2 power minus 2 times 1 to the 1/2, there's a simplification we can make there without using the calculator. How could we simplify that a little?
I don't see it.
Okay. Well, do you remember what is 1? Remember we did that exercise at the beginning of the session today? 1 to the x. What is 1 to the x?
1.
Yeah. So 1 to any power equals what?
1.
That's right. So that's the simplification that we can use here. I know you tried to use that simplification earlier, I think, but I think we made a mistake because we were doing too many steps in our head. But now we should be able to make that simplification. So how is that now going to simplify?
Minus 2.
Let's see. Okay, well, let's go through that. What is 1 to the 3/2 power?
Oh, what? Okay. I think we're just on the wrong page here. Okay, so
what is
2/3 minus 2?
Okay, good. So what is 1 to the 3/2 power?
1.
Good. And what's 1 times 2/3?
2/3.
Good. And what's 1 to the 1/2 power?
1.
And what's 1 times 2?
2.
Good. Now, how is this different from what you did before? I think you were also trying to simplify this before, but do you remember the mistake you made is that when you simplified, you ended up raising the 2/3 to the 3/2 power, and you ended up raising the 2 to the 1/2 power, if you remember that?
Mm-hmm.
Okay. Do you see how that's a mistake?
Right.
Yeah. So the point is that when you do 1 to the 3/2 power, not only the 1 disappears, but the power disappears as well. That's why it's such a useful simplification. We don't just move the power over to the next term, that whole term just disappears. And that's something that's easier to see. So I do think it's actually a really good idea to simplify 1 to any power into a 1 before we pull over the calculator. I think that's a good thing for us to get used to doing. However, we shouldn't do that in our head. It's still a good idea to first write down that we're plugging in the 1. So I think the way we have this written is going to be the safest notation for us. First, write down that you're plugging in a 1, then do the simplification. Okay, so now let's rewrite the first term. The first term in the first brackets we can't simplify without a calculator, so let's just recopy it. Okay, and now we can pull over the calculator. There's no more easy simplifications to make, so now we can pull over the calculator and try that on the calculator. So what do you get when you actually do it on the calculator?
I get something that I don't think is right, but
Okay. All right. Well, then try solving it on the calculator then. I mean, using the integration button.
So x minus 1 divided by square root of x. And then second calc, 7 from 1 to 9. Huh. I get an error. Let me see. x minus 1 divided by square root of x. And when I go to second calc, I go to 7. And I type in my lower limit is 1. My upper limit is 9. I get an error.
Okay.
Weird.
Well, go back to your y equals menu and see if you typed in the function correctly.
X minus 1 divided by the square root of x. Yeah.
Did you put parentheses around the numerator?
Yep.
Okay. Go to Zoom Standard.
One, 9. Aha. Yep. And the answer is 13.33. So I'm definitely way off in my calculator.
Okay. So now the most important thing is to make sure we could get this on the test. So why were you getting that error message before? It's because when you do this on the calculator with the calculator graphing, you have to use limits of integration that are inside of the window. So you must have somehow changed your zoom on an earlier problem so that 9 was not inside the window anymore. So we went back to Zoom Standard. But in general, so if you're getting that error message, you can just go to the window menu and change xmin and xmax so that they include your limits of integration. Does that make any sense? Okay. Okay. All right. So we have the right answer here. Go back to where you tried to do the calculation. Oh, let me actually do one thing on my own. One moment. Okay. So you should still have on your calculator, when you tried, so the calculation was 2/3 9 to the 3/2 minus 2 times 9 to the 1/2 minus 2/3 minus 2. Did you try to do that in one step on your calculator or multiple steps?
Try to do it in one step.
So you should still have that in your calculator display if you go back up to it. So can you find that line where you tried to do that?
How do I go back up?
So you want to hit second and then the enter button. And if you want to go back multiple lines, you keep doing that.
Okay, I typed in.
Okay, and now just read to me exactly what you typed in so I can see where we went wrong.
I typed in a parentheses,
Mm-hmm.
2 divided by 3, another parenthesis, 9, close parenthesis, raised to 3, divided by 2, minus 2.
Now, did you put that exponent in parentheses?
No.
Okay, so that's where we went wrong. So when do you need parentheses on the calculator? There's three situations where you need to add parentheses for the calculator. When there's more than one thing in a numerator, you need to add parentheses to tell the calculator that. And when there's more than one thing in a denominator, you need to add parentheses to tell the calculator that. And when there's more than one thing in an exponent, you need to add parentheses to tell the calculator that. That's pretty much the only times when you need extra parentheses for your calculator. Of course, you still need the same parentheses you would normally use writing it down, but the only times you need extra parentheses is when there's more than one thing in the numerator, more than one thing in the denominator, or more than one thing in an exponent. So the best way to do this is before you start typing it in on your calculator, write down the parentheses you're going to need on your calculator. So for example, let's go back here to what you have written down and let's put parentheses around the 3/2 and 1/2 exponents.
Okay.
And you really only need to do that in your final line, because that's the line you're putting into the calculator. We really only need to do that in the final line, because that's the line we're putting into the calculator. Okay, all right. Well, you can try that later on your own time and see if you get the right answer that way. We know we have the right answer, and we have a method that we could use on the test. I think it would be good to build up your calculator skills for that, but we don't need to spend the tutoring time on that. But that's what went wrong here, not including those. So I would recommend in the future, when you get to the step when you're going to plug something into the calculator, write down the parentheses you're going to need first on your paper. Okay, let's go back to the beginning then and see how we did on this problem. Let's scroll up. Okay, so let's see. We started with the problem, and then you simplified this by rewriting the root x as x to the negative 1/2. And then you used the distributive rule, and you multiplied. Now, how do you multiply two numbers with the same base? How do we multiply two numbers with the same base?
You add the exponents.
Perfect, and that's exactly what you did. So that turned out to be a very good way to simplify this. Then you took the antiderivatives. Okay, and then the point where we, and from that point we were doing well. Remember, the point where we got into trouble is even if you're going to simplify the ones, you should still write down the ones. Start by writing down the ones, and then you can simplify them. Now, you should keep in mind there is one other way you could have simplified that original fraction. You could have rewritten the original fraction as two separate fractions. If you remember that we talked about that earlier too, how would you rewrite that original fraction as two separate fractions?
As x over the square root of x minus 1 over the square root of x.
Yeah, maybe we should write that down on the top of the screen there just for practice. So let's write x minus 1 over root x equals, and write down the other way of rewriting that. Great. Now, how could you simplify x over root x?
X over x, the 1/2.
Excellent. Good.
And then minus x to the 1/2. And then...
Good. And let's rewrite that.
Well, I guess you can just divide. So...
How did you get that 1/2 exponent?
1 minus 1/2.
Great, because how do you divide two numbers with the same base?
You subtract.
Good. Subtract the exponents. Good.
Yeah. And then this doesn't have the same base, so I would just bring this up, and it would be x to the negative 1/2.
Right. Those 1 does not have the same base as x, so you used a different approach. And compare that to what you got the other way.
It's the same.
Okay, good. I'm not saying this way is better. The way you did it was perfectly fine. So you should use whichever of these you feel more comfortable with. On some problems, I think the top method will be simpler, but on some problems, the bottom method might be simpler. So like I said, there was nothing wrong with the way you did it. If that's the method that's more comfortable for you, that's perfectly fine. I just wanted to remind you that the other way is possible as well. They're both good methods. Okay, all right. Well, this would be a good problem to go back and try again. We did have some issues with this. I think this would be a very typical type of question like you might have on the test. So this would be an important one to mark and go back and try again. But let's find some more space.
Okay.
Okay, and we'll go through another problem. So this is the integral from 0 to pi over 2 of sine theta d theta. Okay.
It gives us sine. That would be gives us sine. Derivative cosine can give sine. negative cosine of pi divided by 2 minus parentheses negative cosine of 0. This is all equal to 1. Double check. So y equals sine of x. Graph this. Second calc. 0 to pi divided by 2 equals 1. Good.
Okay, that one went a lot more smoothly. Very good. All right, let's see. Now, one thing that we've been doing really well, you've been very careful in all of the sessions to be very careful with the plus and minus signs. Most people make lots of careless mistakes with those, but I think we've made hardly any or no mistakes with those, and the same thing was true here. So that's good. We want to keep that up. So we want to be very careful here with the negative signs, and you were to put the exact right negative signs in the exact right places. So looks like that all came out correctly. Let's see, anything else? All right, you can't argue with success. All right, let's move on to the next problem.
Okay.
All right, so let's do the integral from 0 to 1. It'll be a fraction. On top of the fraction, we have 2. And on the bottom of the fraction, 1 plus t squared dt. All right, that's the problem.
Okay. This would be so tangent 1. I'm sorry, the inverse tangent. Inverse tangent of 1. So I'm going to divide this by 5. Well, I'll just wait. Okay. Minus the inverse tangent of 0. Okay, I'm going to start with inverse tangent of 1 minus inverse tangent of 0. Same thing. Okay, divide by 5. Wait. Second enter. There we go. Okay. Divided by 0.25, so 1/4. Okay. 2 times 1/4. So let me check. Y equals 2 divided by 1 plus x squared. Graph. Second calc. 0. Okay. Second calc. Okay, cool, that's right. I got 1.57. That's 1/2 pi.
Okay, so what's the answer?
1/2 pi.
Okay. All right, let's see here. So you started by using the constant multiple rule. You took the constant 2 kind of outside and put it in front of the brackets, and you took the antiderivative of 1 over 1 plus t squared to get the inverse tangent. And then in your third line, it's good that you put in an extra set of parentheses. That set of parentheses was good to show that the 2 was multiplying times both terms. Okay, and then it looks like you did a good, careful job to get an exact answer in terms of pi. Okay, well, I think that's some good progress on that. That's good that you were recollecting how to do those problems. I think a lot of students have trouble with those, but we did that correctly. Okay, all right, well, that was a correct process too, so let's just move on. Let's go on to the next problem. So now we're going to do the integral from 1 to 8.
Okay.
Of the cube root of x.
Start that. Is that?
And that's it.
Okay. It's 3 plus 3 3 4 over 3 divided by 4 over 3. It's 3 fours. You add 3 over 3, so you get 4/3 divided by 4. 3 over 4. Simplify further. So 3 divided by 4 times 8 raised to 4, which is 4 divided by 3. That's 12 minus 3 fourths. That's 11. I guess I should. So 44 plus 1. 45. It's 45. That's 25. Okay, I can check this. Y equals cube root of x graph. Second calc. One to 8. I go 1 to 5. 45 over 4. Good.
Okay, so what was your answer?
45 over 4.
Okay, let's review that. Let's see. So I do think it's a good idea before plugging things into the calculator to simplify a little bit, like getting rid of the 1 to the 4/3. So what you did there, I think, was a good approach. Before you plugged the whole big mess into the calculator, you said, well, 3/4 times 1 to the 4/3 is just 3/4. That's a pretty simple simplification that we may as well make. Good. Now, in this particular case, I think, so I'm sure you would get full credit for this. I think it's probably better practice, though, in this case, to give our answer as a decimal. So let's write down the answer as a decimal.
As a decimal. Okay. I guess I'm just not sure when they want a decimal or a fraction.
Okay, so what was the answer as a decimal?
It's 11.2.
Good. I just have to ask you because your screen is lagging behind. I can't, I'm in suspense here. I've got 11 point and it's not written down. All right. Yeah, so to answer your question, when the decimal comes out to be an even decimal that ends, then it's better to give it as a decimal because I think those answers are easier to interpret. Fractions are better when that's the only way to give an exact answer. So if your answer is a decimal that just goes on forever, 11.69843286965543, that's when it's best to write the answer as a fraction because that way the answer is exact. On the other hand, if the answer is a decimal that just ends, then you may as well just give it as a decimal. So that I think is best. I'm not saying you would lose credit here, but it's a little bit easier, I think, to think about your answer in this case as a decimal. I think you have much better intuition for what 11.25 is than for what 45 fourths is. You know, if someone came up to you and said, how would you like to earn 45 fourths of dollars, you wouldn't really know what that meant. But if someone said they were going to give you 11.25, you probably know what that meant. So in this case, I think the decimal is the better form. Fractions are best when that's the only way to give an exact answer. That's not something to sweat about because either I'm sure would get full credit. Just a minor detail. Okay. All right, fair enough. Well, I think it is time to declare victory for section 5.3. I definitely think we mastered that. Well, maybe I shouldn't get too cocky. We had a little bit of trouble with that first problem that we did. If you recall, it's on the other page, but the x minus 1 over root x, I think we might not have gotten that one right. So it's important to go back and try that again. I'm not going to give you more like that right now to save time, but that would be good for you to practice some more on your own. That did give us a little bit of trouble. But overall, I think we're understanding the ideas here for section 5.3. The one problem that gave us trouble today was this one. So this would be a good problem to retry again on your own, because this is pretty typical, and this is going to be the basis for harder problems. So we need to get comfortable with this. So this would be a good one to try again. Except for this type of problem, I think we're in pretty good shape to build on that going forward. This is a little bit different. This is kind of a weird question, or a little bit different question than the ones we've done before. But see if you pay attention to the notation here and try to work this out on your screen. Like I say, this is a little bit different from the problems we've done before, so we can't just automatically repeat. We have to figure out what this means. And then try it on your screen.
And there's no integral sign. There's no antiderivative sign.
That's right. That's how it's different. Good. So what does this mean? What are these instructions telling us to do?
To plug in -3 into the function, and then plug in -1 into the function, and you subtract them.
Okay, that's what they mean. So I just want to make sure we're familiar with this notation. You can use this notation without using integrals or definite antiderivatives. I want to make sure we're familiar with this. So try writing out on your screen how you would do that. Okay, I'll interrupt. We're on the right track, but what this means is first you plug in the top number, then you plug in the bottom number, and then you do the subtraction. So you subtract with the top number gets plugged in on the left-hand term. I think that's something we kind of already knew, but we probably lost our intuition because I was using negative numbers for that. Okay, so I wanted to make, so there was an important clarification there. First, you plug in the top number, then you plug in the bottom number. One thing I wanted to point out here is, well, okay, yeah, so that was correct. There's a little simplification we can make here. Maybe this might be a little trickier than you might actually have to do on the test, so we won't even bother doing it on our calculator. We'll have plenty of time to practice the calculator later. I just wanted to review what this notation meant. I'll go back to my screen. So let me show you the mistake that we've been sometimes making in the past here. The reason I wanted to do this example is that sometimes in the past, you ended up doing something kind of like this. Maybe not exactly like this, but you were kind of making this mistake sometimes. Do you see how this can be tempting? Instead of plugging the -1 into both terms and the -3 into both terms, there were a couple of times where you were kind of plugging the -1 just into the first term and the -3 just into the second. So anyway, this would be a mistake. So I just wanted to warn ourselves against that. We don't want to do that. It turned out there's two different subtractions in this problem. There's the subtraction inside of the brackets. There's the subtraction inside the brackets, and then there's a whole different subtraction subtracting the two brackets, which is what this notation means. It's just important to be careful and not get confused. We've talked about the safest thing is take small steps. Actually write down exactly what you're plugging in. Otherwise, it's easy to get confused. Okay, so I just wanted to clarify that. We also saw it's always first the top number, then the second number in the subtraction. These videos are offered on a pay-what-you-like basis. You can pay for the use of the videos at my website. There's a link to my website in the annotation. The address is www.freelance-teacher.com/videos.htm. Or you can just use the link in the annotation. Thank you.